Welcome to Bonding, Writing Ionic and Covalent Lewis Structures. I'm going to look at what currently this year is question number 5 from WebAssign to start out with. And question number 5 on WebAssign, on mine, it gives me CO2, and the question is, give the total number of valence electrons in each of the following molecules. So we'll have to find the valence electrons in carbon, and then we'll have to find it in oxygen, and in fact 2 oxygens, and then we will add it up. So to find carbon, we go over to the periodic table, and there is carbon. And it says that bottom number there is 4, so it has 4 valence electrons, or you could look at the group number, which is 4A. So there's 4 valence electrons for carbon. Now I'm going to add the oxygens. Let's look at the oxygens. There's O. It says 6 valence electrons. It's in group 6, so it should have 6 valence electrons. So we're going to add 6, but there's 2 of those, so I'm going to multiply it by 2. 6 times 2 is 12, so we have 12 plus 4, and then that equals 16 valence electrons total. Another question on WebAssign asks to identify the type of bonding. So here's one that might be a little bit tricky for you. BaOH2. So Ba comes from here, which is on the metal side of the periodic table, and O and H come from, O is from over here on the nonmetal side, and H is really a nonmetal. So what we have are a metal and some nonmetals. Anytime we have a metal and a nonmetal, it means it's ionic. But if we have 2 nonmetals together that are bonding, that means it's covalent. Covalent. So the bonding in BaOH2 actually has 2 types of bonding. It has both ionic and covalent types of bonds. So now let's practice writing the Lewis structure for magnesium fluoride, MgF2. So first of all, we have to identify, is it an ionic compound or a covalent compound? So first of all, we look at Mg. And we identify Mg is from over here, so it is a metal. If we have a metal, it must be ionic, but let's double check. F is from over here. It's a nonmetal, so we have a metal and a nonmetal, which means it is an ionic compound. We will not have 2 metals together. So how do we write the Lewis structure for this? We take Mg and write it by itself, and then we look at Mg and we go up to the top and we see it forms a +2. It likes to lose 2 electrons to form a +2. And those 2 electrons must go somewhere. In fact, they go to the F. F over here has 7 valence electrons. It needs 1 more to make it 8. So those 2 dots go to the F, but you need 2 Fs since they each need 1 electron. And we're going to put brackets around this. And then we have to show that the F gained, each F gained 1 electron, and there's 2 Fs, to have 8 valence electrons around the outside. And when it gained an extra electron, it came, or had a charge of -1. And F does have a charge of -1. So your final answer would be Mg +2, or you could write 2+. Nothing in between there. And what I mean by nothing in between there, we don't have anything written here. And then we have 2 Fs, it has to be in brackets, has to have 8 dots around it, and then the charge that you'd see on the periodic table. And that's how you write it for ionic. This shows that electrons were completely transferred. They are not shared at all. Let's write the Lewis structure for lithium chloride. So the first thing we do is we check out Li. Li is over here, the metals, so it must be ionic, but let's just double check. Cl is over here, and it is a nonmetal, so it's ionic. When we write ionics, we separate them out. Li is here, Cl is over there, and really and truly every nonmetal in an ionic compound is going to have 8 valence electrons around it. It has to have brackets. It's keeping those electrons in there. And then we look at the charge, and the charge on Cl is a 1 minus. So we write that 1 minus there, and we look at the charge on Li, and it's a 1 plus. It loses its 1 valence electrons to become a 1 plus. And your final answer is Li plus Cl with 8 dots around it and a minus charge, and the Cl has to be in brackets. Now let's write the Lewis structure for SiBr4. Find where Si is. Si is right here, so it is going to be considered a nonmetal. I know it's a transition metal, but it's going to be considered a nonmetal here. And Br is right there. So we have 2 nonmetals together. This is going to be a covalent bond. And we look over here. Usually the one written first is the one that goes in the center, and the one that there are more of usually goes around it. So Si is going to be in the center. And then we just start with single bonds, because everything will have at least a single bond. And I spread the BRs out as far apart as possible as I could in this dimension. And now I have to do the perfect and the actual. So to do the perfect and the actual, I'm going to write SiBr4 again. I'm going to do the perfect on the top. I'm going to do the actual on the bottom just to keep them separate. So if Si were perfect, it would have 8 valence electrons. Almost every atom has 8 or wants 8 to be perfect. If Br were perfect, it would have 8 electrons also, but there's 4 of them. And I got that 4 from right there. And now I add those up. So 8 times 4 is 32. 32 plus 8 is a total of 40. Now I'm going to do the bottom. Si, if S, we're not doing perfect, we're going to do actual. So Si actually has, look at the bottom number, it has 4. It's going to write 4 plus, I'm going to look for Br. Br, the bottom number is 7. And you look up there, it's group 7. It actually has 7 valence electrons, but there's 4 of them from that 4 right there. So 7 times 4 is 28. 28 plus 4 is 32. Now I'm going to do another math problem. I'm going to do 40 minus 32. I put the perfect on the top, so your bigger number's on top, and then the smaller number's here. So you should never get a negative number, and you should never have an odd number. So 40 minus 32 is 8. Our next step then is to take that 8, divide it by 2 because the atoms are sharing 2 electrons, and 8 divided by 2 is 4. So that tells me we should have 4 bonds or 4 lines for this compound. And we do. We have 1, 2, 3, 4. If by chance it had said 5 bonds, we would have to add an extra bond somewhere, and it could have been on any one of those. So one of those would have had a double bond. Now the last part is we have to look at this number 32. Our lines and any extra dots have to add up to 32. So let's check what we got. We have 2 here because each line represents 2. So we have 2, 4, 6, 8. We have a long ways to go to get to 32. And in general, what you need to do is just add dots so everyone adds up to 8. So now this bromine has 2, 4, 6, 8. We'll go to this one. It had 2 from that line, then 4, then 6, then 8. Now this one has 2, 4, 6, 8. And then we'll go to this one. It had 2 from the line, then 4, then 6, then 8. Now these should add up to 32. Let's check. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. It added up to that 32. And that is our compound. Now we're going to look at CO2. Again, we have to verify if it's an ionic compound or a covalent compound. So we look at C. C is over on the nonmetal side, so this must be a covalent compound. If you're starting with a nonmetal on the left-hand side, it usually is covalent, but let's check. O is also over here on the nonmetal, so it's a covalent compound. Let's write out our stick structure. So we have a C and an O and an O. I drew them as far apart as possible. Now we have to do the perfect and the actual. So if carbon were perfect, it would be 8. If oxygen were perfect, it would also be 8, but there's 2 of those. So that's 8 times 2 is 16. 16 plus 8, I believe, is 24. Now actually, carbon is there. Carbon actually has 4. And oxygen actually has 6. But there's 2 of those. So that's 12 plus 4 is 16. So we have 24 minus 16, which must be 8. And then we do 8 divided by 2 equals 4 bonds. 4 bonds? Are you kidding me? This one has multiple bonds in it. So we could do a 2 on each side. We could also do a 3 on one side and a 1 on another side, or we could do 3 on this side and 1 bond on that side. And again, we have to get all of our dots or lines to add up to 16. So in this first one, we have 2, 4, 6, 8. I'm guessing we need 10, 12. Those are some cranky looking dots. So if you have 2 lines, you just need 2 sets of dots. On this one, we just need 1 set of dots, and this one we need 3 sets. And then this is just the converse of that other one. And what we have to draw on these, I should have written them that way, but I didn't have space. And you draw these half arrows between them, representing that they could fluctuate between all of those structures. They're called resonance structures. Resonance. Hopefully this podcast has helped you determine if you're working with an ionic compound or a covalent compound. Ionic compounds always start with a metal like NaCl, and they are written completely different because electrons are transferred in those. They are not shared. And covalent compounds, for example, maybe NCl3, they have lines with them to show that electrons are shared. And then they will almost always have extra dots to add up. And where we find the perfect and the actual amount from is from the periodic table. Almost everyone is perfect at 8 except for hydrogen. Hydrogen's perfect at 2, boron's perfect at 6, the rest of them are 8. And to find the actual, you look at the bottom number in the box, or you look at the A group number. I hope this has helped. I will see you soon.